Okay, let's focus now on this third integral here. This is a very important integral. And in calculus 2, you will see that actually you can compute this integral, and the value of this integral is the square root of pi, okay? As I said several times along the course, we don't have tools to prove this result, but this is a very important result. And you will do it in calculus 2 because the way to do it is, the standard way to do it is to introduce integrals in several variables and then reduce to this integral here and then prove that this is actually the square root of pi. But that's not our concern here. Our concern is whether the integral converges at all or not, right? So we have to prove actually that it converges, because if this is the square root of pi, it is of course a convergent integral. So let's see. The first thing we need to notice is that this integral here is an even function because it depends only on x squared. And the interval here that we're dealing with is symmetric. So actually, we could write this integral as twice the value of the integral in half the interval, even if the interval is infinity. If this integral here diverges, then this one diverges. If this one converges, then this one converges. And the value of this one is twice this one here. Sorry, plus infinity. Okay? Right. There are actually two ways to prove this. Well, there are more, but at least there are two ways. Let's forget about these two here. Just focus on this integral here, okay? We're going first to use the comparison test. And we're going to compare this with an exponential. The reason is, if you plot this function in the positive side, this function looks like a Gaussian bell, something like this. Right? It goes very fast to 0 because the argument of the exponential is a square, right? If you compare this with the exponential of x, so this is e minus x squared. So if you compare with the exponential of x, which also starts here, this value is 1, right? The exponential of x goes like this. It also goes to 0 very fast. It crosses this one at the point 1, okay? Because for x equal to 1, this one here, which is the exponential, is e minus 1, same as this one, right? So they both cross at the same point, e minus 1, okay? But this one here is below this integral, or below this function in this region, and it's above the function, it's an upper bound in this region here. So that is exactly what we're going to do, to use this as an upper bound here. And for that, we need to get rid of this first interval here. So the first thing we're going to do is to split the integral into pieces, right? Like this. Okay. There is no problem with this one because this is an ordinary Riemann integral and the argument is a continuous function. No problem. I mean, this gives you a number, whatever. And so we only have to worry about this integral here. Okay. So let's focus on this one. And now we have this nice bound. The bound is obviously if x is larger than 1, then x is smaller than x squared. That is trivial, right? So minus x is larger than minus x squared, and since the exponential is an increasing function, e minus x is larger than e minus x squared. So this is an upper bound, as I said, and as it is shown in this picture here, right? So this integral here, whatever it is smaller, strictly smaller than this integral here, from 1 to infinity of this exponential. But well, you can calculate the primitive of this and prove that this is finite. This is trivial, right? Actually, we did it in an exercise. So this one is finite, therefore this one is finite, therefore this one is finite, therefore the original one is a finite integral. So it's a convergent integral. Okay, this is one way to prove this. It's not the only one, right? Because if you get to this point where you have to prove the convergence of this integral here, what you can do is a change of variable. So having a x squared here is very inconvenient. So one thing you can do is to change from x squared to t. So you do this change of variable, right, to t. which means that x is equal to t 1/2. All right, so dx is equal to 1/2 t minus 1/2 dt. Okay, so what you have here is the integral from, the limits are again 1 to infinity, right? Because for x equal to 1, t is 1. For x to infinity, t is infinity, right? And what we have is this integral here. And if you remember, we have analyzed this already. The integral from 1 to infinity of the exponential times any power of t is always finite. Doesn't matter what the power is. So in particular, it doesn't matter whether the power is minus 1/2. This one here is a finite integral. So either way that you want to analyze it, the result is the same. The integral is converging.